All right, good morning, everyone. So today we're going to continue our discussion of gradient descent, or of what we're doing with gradients, which is gradient descent. So just to sort of review, we've seen some of this stuff before, but the main motivation for looking at gradients is that we know that when you have a cost function and you're looking for either the minimum or the maximum, if this cost function is smooth, meaning the gradient exists everywhere, and if you are looking over an unconstrained interval where you're not saying that the parameters need to be, on one side within some constrained set. So if we look everywhere and we ask, where can I find the minima or the maxima, then you can see they always exist at points where the gradient equals 0. So that's our main motivation. But to be a bit more detailed, when we talk about places where the gradient can equal to 0, we call those stationary points. And as we've seen, there's a couple kinds of stationary points. There's minima, there's maxima, but there's also a third kind of stationary point, which is called a saddle point. In a saddle point, two different kinds of saddles are illustrated here. So if you look at this point in 2 dimensions, you would find that the gradient at that point right there is exactly 0. So in other words, the slope in any direction at that point is 0. However, you can see it's neither a minima or a maxima. It's a saddle. And in this particular case on the left, what's happening is the function is curving upward in one dimension and curving downward in the other dimension, and this is the point right in between. Now here's another example of a saddle, which is even stranger, because in this case, when you look right at the saddle point, not only do you have 0 gradient, but you also have 0 curvature. So the function is not curved in any way right at that point. So anyway, these are the 3 possible explanations for why you have a gradient equal to 0 at some point. So in many cases, we can say, based on our knowledge of the function we're minimizing, that we only have minima, and so when we look for these points of 0 gradient, we're guaranteed to find minima. However, in other problems in machine learning, we don't really know whether we can get stuck at a saddle or a minima, and so we have to be careful and have to use other numerical tricks to try to escape saddles and converge to minima. So, so again, our main goal is finding the parameters W that set the gradient to 0. And usually, we can't do this analytically. We can't do this on paper. So we have to resort to an algorithm to do this. And so today, that's kind of the subject of today's lecture, are some algorithms to try to find that gradient zeroing parameter vector W. Okay, so the simplest and most basic algorithm, on which a lot of other algorithms are based, is called gradient descent. And so just to set up the problem we're trying to solve, so our goal, again, is to find the minimizer of some function. So in other words, the W hat, that is the minimizer JW. Often we call this the objective function or the cost function or the loss function. We're focusing on unconstrained minimization because we're not imposing any constraints on this vector. W here in this minimization. And we're also assuming for this algorithm that the gradient exists everywhere, so we don't have any issues with computing it. There are some problems that we have encountered, like the lasso problem, where this is not true. The gradient does not exist at the origin in lasso, and then for that reason, you cannot apply a technique like gradient descent, so you have to do something else. Okay, but assuming that it does exist and we can take gradients, then the gradient descent algorithm goes like this. You choose some initial guess. We'll call it W superscript 0, and then we iterate the following line. You set your new parameters equal to your old parameters minus a small scalar, we call it step size, times the gradient at the old parameters. So this picture on the right illustrates it. So we start here, take a gradient step, which means we travel a short distance in the gradient direction. Remember that the gradient is always perpendicular to the contours, so that means we're traveling in this direction, perpendicular to the contour at that point. But as you can see, the distance we travel matters. If I moved in this direction, but I moved all the way over here, then my new cost would actually be higher than my old cost, so that would be bad. So I want to move a small amount. We'll talk more about how we choose that small amount, but I want to move a small amount here in the direction of the negative gradient. And then that brings us to the next iteration. So then we're at W1, and now we move a small amount, again perpendicular, and that brings us to W2, and so on. And if we keep doing this, then as we'll see, we can prove that we will converge to a minima, or at least the closest minima to where we started. So this parameter, alpha, is an important parameter. It's a positive parameter. It's called the step size of the learning rate. It has to be positive, and it should be small enough. And in words, we're just going to take downhill steps until we reach the bottom. As for how you choose that first point, most cases I would say it's chosen randomly. Sometimes if you choose it in a deterministic way, like you set it at 0, you might run into trouble because perhaps the cost function has a 0 gradient at the point 0, and then you're stuck there. So by choosing it randomly, you can escape those weird conditions like that. All right, so this is the gradient descent algorithm. Any questions on the algorithm? Okay. So let's do a quick analysis of this to convince ourselves that this actually works. So again, we start with the Taylor series expansion of J at or about a reference point. In this case, WK will be the reference point. And I just want to emphasize over here, the K's in the superscripts, those are the indices of the iteration. Those are not, taking W to a power. We're using superscripts because we have a lot of examples of subscripts, and so we just don't want to confuse this with like the kth W vector in the W matrix or something like that. Okay, so here we have the Taylor series expansion, which we know is a way of writing J as a function of an arbitrary W, relating it to what happens at a reference point WK. So we have the cost at the reference plus the gradient inner product with the deviation from the reference, and then all the higher order terms are collected here. This is our big O. So this again means that for W close enough to WK, this term is at most a constant, call it C, times this norm squared. Okay, so now we would like to use this Taylor series expansion by evaluating it at the specific point w equals wk plus 1, which in a gradient descent is the next iteration. So all I'm going to do is plug in wk plus 1 all these places, and we get this new expression. And then we can go one more step further. We know that in gradient descent, by the definition of the update, we can write the difference between wk plus 1 and wk as the negative alpha times the gradient. So that means I can replace this and this with that negative alpha gradient. And when we do that, you get this expression here. And we can just make some further simplifications. We have this term here, which is, you can recognize this, a vector transpose itself is just the squared Euclidean norm of the vector. And for this last term, actually, it helps. Let me write it in a slightly different way. I think it makes it more clear. Let's put the big O over here and the alpha k squared over here. So essentially what I've done is I've treated this as just a constant scaling, and I've taken it out of the big O. And at that point, we have this term multiplying this constant. And now, if we step back and say, okay, what does this tell us? Remember that our objective in taking this gradient descent step is to make the new cost less than the old cost, right? So that's what we hope happens. We hope that jwk plus 1 is smaller than jwk. Over here, we see a term that helps us achieve our goal. This term is definitely negative because the norm is definitely non-negative, and this is non-negative. So overall, this is, it would be 0 if we're exactly at a gradient zeroing location, or otherwise it's strictly less than 0. So this is helping us achieve our goal. On the other hand, this last term, as you can see, this is a positive term. This is preventing us from achieving our goal because it's actually increasing the value of the cost. So in order to say that overall our scheme is working, we have to argue that this second term is going to overwhelm the third term. And if the second term overwhelms the third term, then overall this is negative, and overall we have decreased our cost. So how can we justify that this second term is going to overwhelm the first term? So for this, we can again appeal to the definition of this big O. So when we see big O of alpha k squared, we have to remember what that means. It means that for small enough alpha k, we can upper bound this by the term c alpha k squared. So this is less than or equal to c alpha k squared for some c. Okay, so when we have that, we get this upper bound like this. And now we can make a direct comparison between these last two terms. They have the same norm squared. The first one has minus alpha k, the second has c alpha k squared. And now you can see that it's always possible to make alpha small enough that this term, this alpha k, is larger in magnitude than this, right? Because remember that when a alpha k gets really small, this squared term gets much smaller than the linear term. So, so we can, by making alpha k small enough, we can always guarantee that this will overwhelm this. We can do this no matter what that constant c is. I can always find an alpha k. You give me the constant c, I will give you an alpha k that's small enough so that this holds. Okay, and then finally, middle term will dominate the last term, and we find that after taking our descent step, we have decreased our cost, or in the worst case, we have not increased it. Okay, yeah?
For consistency notation, is there any reason why alpha k is not an alpha superscript? Because it changes at every 5 step, right?
Oh, yeah, we could have put it in the subscript. I guess we do end up squaring it sometimes, so that would get a little messy. So I think that's part of the reason why it's in the superscript. Whereas we're never going to square a vector, so it's kind of safer to do that. Yeah, but yeah, sorry about the inconsistency. Okay, so this is making sense. Why? So this is giving us a justification that, yeah, this really should work. We should, for a small enough step size, we should be able to decrease our cost with every step, and then converge to, hopefully, to this minimum point. Okay, but we have to be a little bit careful to make a distinction between local and global minimum. So here we have a function where, as you can see, there's different minima, different maxima. So if our objective was to minimize this function, then ideally we would find this point. But if I started anywhere in this range here and I did gradient descent, what would happen is I would converge down to the center of here, and I would not find this. And so you would say we found a local minimum, but we didn't find the global minimum. So this definitely is an issue in machine learning in some cases. The place in machine learning, or the instances where it's not an issue, is when we have what's called a convex function. We'll talk more about convex functions a little bit later, but whenever we have a convex function, basically any local minimum is also a global minimum, and we don't have to worry about this. And examples of convex functions that we're minimizing would be our least squares cost, our ridge regression, alpha, logistic regression, regularized logistic regression. So basically, everything we've seen so far is convex, and we can essentially not worry about this local versus global minima issue. However, when we get to neural networks, we do have to worry about this, and it's very easy, if you don't code things right, to get trapped in a bad local minimum. So it's good to keep this in mind, and it's good to be aware of when it's a problem and when it's not a problem. So convex functions, again, we'll define what that means later, but convex functions, it's not a problem, but more generally, it is a problem. Okay. Any questions about this? Yeah.
So for non-convex functions, would it help if you basically change the initial?
Yes. Yeah, exactly. If, like in this case, if we're minimizing this and I start anywhere in this region, then with a small enough step size, gradient descent will take me to the global minimum. So choosing the initialization wisely is one of the strongest things you can do to try to encourage convergence to a global minimum. There's other tricks, as we'll see. Sometimes by actually, it's maybe counterintuitive, but by using a very large step size, you can bounce out of the shallow local minima and bounce into a good deep global minima. And so you'll do something like use a large step size at the beginning, and then that will hopefully get you into basin of attraction of a global minima, and then you use a smaller step size, which helps you settle to the bottom. So those things, again, we don't have to worry about now, but we will talk about them in the context of neural networks. Okay, great questions. Any other questions? All right. So now that we have this technique, gradient descent, we can attack our motivating problem, which is this binary logistic regression problem. So we want to find the parameter vector W, that minimizes this cost function. So this is the cost function that we derived in the last unit, the cross entropy loss. So just to remember, this is our parameter vector. We're using W0 to represent the intercept term instead of B, just to make the notation simpler. And so this would be for the ith data sample, we have this 1 and then the features. This gives us the ith score. And then the cost is a sum over all the I of this thing that we derived in the case that Y is 0 or 1. Okay, so we would like to apply gradient descent. So the main thing we have to do, the main thing that's challenging is we have to compute the gradient of this with respect to the parameters W. So we want sort of an organized way of doing this. So the way we're going to think about this right now is we're going to think about this cost as really like a two-step procedure, a composition of two functions. First, there's a function that takes W and makes the Z vector, all the Z's. We'll write it this way, boldface Z. And in particular, that function is just the matrix A times W. The matrix A, like back in unit 1 and 2, looks like this. The second thing is once we have the Z's, there's another function, we'll call it F, which implements this. And so the main structure we see here is we see that this is a sum of scalar functions of the individual Zi terms. So we can write them as Fi, like this. So again, first stage is W to Z. That's a linear transformation. Second stage is all the different Zi's operated on non-linearly by this function, summed together to get our final cost. So this is a separable nonlinear function. Together, they give us the overall function from W to J. Decomposing it in this way helps us to compute the gradient. In particular, we can use this thing called a multivariable chain rule. And the multivariable chain rule, we're seeing it for the first time here, but we will see this a lot as we, in some of the later units, because this is the main workhorse equation that is used to train neural networks through many, many different stages of linear and nonlinear functions. So what we're seeing here is actually a simple preview of what we will see later. So, okay, so here we go. So if you want to compute the gradient with respect to, now this is just going to be the derivative with respect to one of the J's of J, or you could say F of Z of W. Essentially, you want to think of the different ways that information can travel between Wj and F. So let me just draw a little picture. So this is, imagine Wj is here. Wj has an effect on all these different Zi terms, and the Zi terms all have an effect on the final function, either F or J, however you want to think about it. And so when computing this gradient of F with respect to Wj, you want to think of the gradients along all these different individual paths. So that's how we can think about this. So the rule says you sum over all the paths, and then for each path, you have df dzi, dzi, dwj. Okay, so whenever you encounter one of these sorts of problems, the main question is, where do the sums come in? How do I formulate this multivariable chain rule? Just draw a quick picture of this little kind of flow diagram or computation diagram here that shows how the information flows through your network. Okay, so again, this is a super important rule. that we're seeing for the first time here, but we'll use it extensively later. Okay, so in this case, how do we apply it? So we have to figure out these two terms. So the first one, what is df dzi? So coming back to our equation, all right, so first of all, if I'm looking at just a particular I, then there's only one term in the sum over many I that matters. And the term that matters is the term with the same I as the one I am differentiating with respect to. So I'm going to have this, and now what is dfi dzi? We can figure out that from this equation. So again, I have to use the chain rule, but I would first take the derivative of the log, which is 1 over 1 plus zi, and then I take the derivative of what's inside the log, which is going to be e the zi, and then I take the derivative of this with respect to zi, which is minus yi. Okay, and then with a little bit of rearranging, what we can do is we can maybe divide top and bottom by e to zi if we want to write it like this, a little bit cleaner. Second question is, what is dzi dwj? So for this, we want to think about this equation over here, and maybe it helps to make a little picture out of this. So we have a matrix A, we have a vector W, and we have an index down the rows of A will be I, the index across the columns of A, and down the rows of W will be J. And so now we're asking the question, what is the derivative of the ith Z with respect to the jth W? So for the ith Z, I'm only going to involve the ith row of this. For the jth W, I'm only going to involve the jth column, and there's basically only one term that matters, which is the ith row and jth column of A. Other than that, it's linear. So that's one way to think about it. Another way to think about it is you just literally write out Zi in terms of the elements of J. You would have an equation like this, and then from here too, you could immediately see how this derivative comes about. Okay, so those are the two things, and then we can put them together. You know, obviously we just take those two terms, insert them in here, sum together, and that is our gradient. Okay. All right, any questions? All right, so let's see how we would do this in Python. So we're actually going to see a few different versions of this, different ways to implement it. But what's in common is this way of breaking up the computations into two stages. The first is called the forward pass. The second is called the backward pass. The idea is that when you compute these gradients, it very much matters where you are evaluating the gradient, right? Like if I take the gradient here, if I take the gradient here, that's a different value than if I take the gradient here. So I first have to figure out what is the point I'm evaluating the gradient at. Second, I take the gradient. And that's especially an issue here. Like if I want to evaluate the gradient of f at a zi, I first have to figure out what is that zi. To figure out what that zi is based on my current parameters w, I have to first compute z in this way. So this is in the forward pass, we basically compute all the things without taking derivatives. In the backwards pass, we evaluate the derivatives at the locations we computed, or at the values we computed. Okay, so in this case, forward pass, we first compute, we start with w, we compute this intermediate variable z, or vector z, and then we can compute those individual costs, fi, and then finally we can sum them together to get j. In the backward pass, we are now ready to compute our gradients because we know the value of z because we already computed it. So first, I want to take the gradient of j with respect to wj. We know from the previous page, multivariable chain rule, this is the sum over I, aij, gradient of f at the z vector, and now we're just looking at the ith element. And again, this z was computed in the forward pass. And furthermore, we saw the expression for that looks like this. And so this is what it looks like if we ask for what's the gradient with respect to the jth element. If I want to look at the full gradient, then what I would like to do is expand that out, stack all these guys together in a vector. And if you think about this, based on the form here, this is actually going to give us a nice clean expression of A transpose times the gradient vector of f as z. So this is because, so as we go down this direction, this is indexing the variable j, right? But the variable j is not accessing the rows of A, but the columns of A. However, if I transpose A, now j is accessing the rows of A transpose, and I is going across this direction of A transpose, and that's what we want because I is going to be coming down the gradient vector here. So again, this is an exercise we saw first on homework 0, where I give you like a summation type expression, and then I ask you, can you rewrite this in terms of vectors and matrices? So it's one of these problems. And the reason we want to write it this way is when we compute things, it's so much faster in Python. It's so much faster to implement things in terms of vectors and matrices than it is to do this stuff in terms of for loops. It's like a factor of 10 or maybe more than that faster. And in a lot of machine learning problems, as you already started to see in the last lab, some of these vectors and matrices get quite large. And so computation is an issue. So you want to be as efficient as possible when implementing things. Okay, so this is all the math. Any questions on that? So let's take a look at the implementation. So the first way we're going to do it is we're going to define a function. So you give it the name of the function, you give it the inputs to the function, and then at the very end, you tell it what you want this function to return. And you can return more than one thing if you like. So here we're going to return the cost as well as the gradient evaluated at the vector w that we're inputting and also using the x and y data that we're inputting. Okay, so the first thing we have to do is construct that A matrix because that's what we're using over here. So that's relatively easy. We just use this column stack. We stack a vector of 1s next to our matrix X. And then we want to do this matrix vector multiply. That's what we do with the dot command like we saw last week, I think. Now, the next step is to compute this. Oops, sorry, let's see. I want to compute this quantity, which appears both in the gradient, as you can see, but it also appears over here. Right? Those are the same quantities. So if I can compute that quantity once and reuse it twice, that would be to my advantage. So, and Python, if we give it a vector z, and we put it through those operations, it is with Python broadcasting, it is able to interpret it properly. So here we can see we just give it 1 divided by 1 plus numpy x on the negative vector z. And it's going to give us a whole vector. We're going to call it py. You can interpret it as like probabilities. It's going to give us a vector py. And then finally, once we have that vector, we can use it. Okay, so we can use it in this expression. So we're going to take the log of that vector, And then we're also going to add this term. So here's the log of that vector, and the second term here, this is also done with gradients, so we're going to give it a vector of y's, a vector of z's, and it's going to interpret this asterisk as a pointwise multiply, and then we're summing over that vector to get j. So that's how we're doing this. So the forward pass is here, and then the backward pass is here. So for the gradient, we once again take our py. Now we subtract from it a vector y to get the gradient vector. And finally, we can implement the gradient like this. We have a transpose, so the dot t, NumPy interprets that as the transpose. So you take that matrix, and then you do this dot times this vector. That gives you this matrix vector multiply. Okay, so it's an efficient implementation. We're not recomputing things. We're computing things once and using them again. And finally, we're returning both the cost and the gradient. And the reason why we're returning the cost as well as the gradient, because this cost is very useful for many different things. As we'll see, it can be used to check to make sure your gradient computation is consistent with your cost. But it's also, when we run gradient descent, we would like to see the progress of the algorithm over the iterations. We want to check to see, is this thing finished converging, or does it look like it still needs more iterations to converge? And so that's why we want to return the cost. Okay, any questions on this? All right. So now, when we haven't implemented gradient descent yet, but eventually when we implement gradient descent, we would like to pass in a function sort of like this, but that function should only be dependent on w. We're going to hide the details of the x and y once we give this to a generic gradient descent solver. So we want to just make this a function of w alone. So there's a couple different ways to do that. One way to do that is using something called a lambda function. And if you're familiar with MATLAB and anonymous functions in MATLAB, it's exactly the same thing. So in MATLAB, if I have a function of, let's say, 3 things, and I want to hard code the dependence of these things and just make this a function of this one, I just put this at w in front of it. Python, it's almost identical. You just put lambda w colon in front of it. And now this new thing, jeval, is a function of w for the fixed xtr and ytr that you had at this point. So for example, if I want to evaluate the cost and gradient at some vector w0, I would just do that. Okay. This is going to help us because later we want to pass this function into a gradient descent solver. So this is, this is exactly the same function from the previous page. All right. So, all right. So yeah. So here's our lambda function right here. Okay. Any questions on this? All right. So there's another way to do this that's a bit more sophisticated, and it's something you will see more and more of, especially once we get to the PyTorch and the deep learning. And it's creating what we call a Python class. You could say it's an instance of object-oriented programming. And in object-oriented programming, you make containers that have many different things in it. Those containers could have functions in it, they could have data in it, and so on. So here, we're making this thing called the logistic function. And as you can see, one of the things it's going to have in it is this jeval, which is essentially, it has the same guts as this, but you can see it's not taking in x and y, it's only taking in w. So this is an alternative to that lambda method. So this is one of the things inside this logistic function class. But the other thing that all these classes must have is they must have some initialization routine. It's called a constructor. And the constructor is something that is run when you instantiate this class. So for example, when in scikit-learn, we've been doing linear regression. The very first thing we do is we just call linear regression without any arguments, right? And that instantiates the object. Essentially what's happening is you're running this piece of code, this init code within that class. And now it has set up, it's going to set up a bunch of stuff. So in this case, in this initialization code, when you construct it, you pass in some data. Now, sometimes, in some cases, you don't, for some classes, you don't need to pass in anything. In this case, we must pass in our X and Y training data, and then our constructor sees, okay, it expects X and Y to be given, and then what it does is it takes X and Y, and it makes them parameters that it knows about. So self.x means, okay, anywhere I go inside this logistic function, self is going to contain those parameters. So when I'm inside here, even though it's only taken in W, because this is implicitly part of the same class, I can access all these self objects here. Okay, so this is what we're doing, is we're setting up X, Y, and A. Now you can see we've also created this temporary variable n within this, but n will be forgotten. It's because I'm not doing self.n, I won't have access to n down here. It's not an issue, but it's just a comment that because it's not self.n, it will be forgotten. Okay, so now that we've set up this class, we first instantiate it. We'll call this instantiation log fun. And then when I want to access this method or this function within the class, I do logfun.jeval, and then I pass in what it expects, which is a W vector. Okay. And this is exactly how we had been using logistic regression, or how you will be using logistic regression, but like linear regression. You would instantiate it, and then you would do like linreg.fit, and you'd give it the data, right? That was an example of this, where it has a fit method, but then it also has a predict method and many other methods. Okay, so this is the object-oriented approach, and it's more powerful, and yeah, if you can learn to code this way, it's really nice. Okay, any questions on this? All right. So just as a warning, it's very easy to make mistakes when you're coding gradients, or even when you're deriving gradients, right? Like we had to do all this derivation here to derive our gradients. It's easy to make a mistake somewhere when we do this. And so we always want to check to make sure everything is consistent. And one of the things that we saw earlier based on our Taylor series expansion is when you look at the Taylor series for vectors that are very close together, this is a very good approximation. So as a way of checking, I recommend taking two random, okay, let's say you make one random vector, W0, and then you pick another one that's very close to W0, but again, it differs from W0 using a random perturbation. So we have a very small step size here, 1e minus 6 times another random vector. So now W0 and W1 are very close together. So then what we can do is you evaluate your gradient, and then you take this inner product from your gradient and the difference, and you expect that to be equal to this difference between JW1 and JW0. And so essentially, that's what we're doing here. We're taking the gradient at both points. We're computing this, this last thing here, and then we're printing out the values. And you can see to 5 digits of precision, they're identical. Okay, so how many digits of precision you will get should depend on this step size and actually there's this other order term, and of course it depends on this, but if you make these close enough, then that higher order term can be ignored and you get very good agreement. So you'll have an opportunity to do this in the lab for Unit 6 because you're going to have to do some derivations on your own of the gradients, and they're very easy to mess those things up. And also you could have a coding mistake too, right? So this is a way of just checking to make sure everything is consistent, and then you can, once this is working, then move on to actually the gradient descent algorithm. Okay, all right, any questions on this? All right, so finally, we're ready to do gradient descent. So This is just, the implementation is just a simple function. We're going to give it this jeval, which is itself a function. And remember, this jeval, what it does is we give it a vector, and it passes back the cost and the gradient at that vector. We also must initialize the algorithm, so we're going to pass that in here. We have to tell it the learning rate. So here, by saying equals 1e minus 3, we're setting the default learning rate so that we were making this an optional parameter. The user does not have to specify the learning rate, and if they don't, we'll assume they want to use 1e minus 3. And same thing, this is the number of iterations. We'll assume they want to use 1,000 iterations if they don't tell us otherwise. So in the code, first thing we do is we initialize. We set w0 equal to w init. We declare a history dictionary. This is a way that we're going to collect the information as we run the algorithm. We're going to collect the vector w at every iteration as well as the cost at every iteration. And here is our for loop over the iterations. So at every iteration, we compute the cost and the gradient. Here's our gradient descent step. We're just overwriting the value w0 here. The new version of w0 is the old minus the learning rate times the gradient vector. And here we're just saving those values in the history object. Let's see. And then the very last thing, I mean, there's many different ways to code this, but here what's done is we're converting these. These are not going to be NumPy. This is not a NumPy type format. Here we're converting these things to a NumPy format. And finally, we're returning the last version of the parameters, the last cost, and the history object. Okay. Again, the history and the history is useful to understand how your optimization has proceeded. All right, any questions? All right, so let's take a look. What happens with logistic regression? So, as I described earlier, it's typical to use a random initialization, so we're just going to use zero mean Gaussian unit variance parameters. So we're going to rename this logfung.jeval. We're going to rename that jeval, and then this is optional, just so that we pass it in here as jeval. We're going to set our number of iterations and our learning rate, pass them in here. And then we run this, and it runs for a little bit, and then it passes back the parameters. And finally, we can plot. We're going to use here a semi-log scale for the number of iterations. We're going to plot the iteration number versus the cost at that iteration. And when we look at this, we see, okay, yeah, it's doing a good job of descending, but it doesn't look like it's finished, even after 1,000 iterations. It looks like it's still decreasing. It has more work to do. Even so, we'll stop it there and evaluate how well this is working in terms of prediction, accuracy. So we're going to make a little prediction function here, which takes in some, feature matrix, our weight parameters. And so now here it's computing the score vector z. It's thresholding the score at 0 to give us these binary y hats and returning the y hats. So we can use the test features and the w we got from our optimization to compute y hat, and then we can do a comparison between y hat and the true test labels. And these are logical variables, so either they're going to be 0 or 1. And just by looking at the mean of those binary outcomes, you can compute the test accuracy. And okay, so we find it's 96.8%. It's basically not great. We can do better. And the main reason is that, at least in 1,000 iterations, this thing has not finished converging. And we might be a little disappointed because we might think, well, 1,000 iterations is a lot of iterations. Why is this thing not finished converging yet? Is there something I can do to make it go faster? So the main question then is, okay, well, what about this learning rate parameter? How did I choose that? Maybe that was just a guess. Maybe I should try other learning rate parameters and see how they behave. So here's a comparison of 4 different learning rate parameters. So we have 1e minus 4, which we used on the previous page. We can try an order of magnitude smaller, an order of magnitude larger, and then one that's even a little bit larger than that. And so what we see is from the one from the previous page is the orange. And then, okay, if I use a smaller learning rate, then I get the blue curve, and you can see this one is taking even longer to converge, and after 1,000 iterations, it's even worse than the previous page. Okay, what if I make it faster? What if I change it to 1e minus 3? Okay, so you can see the green curve does seem to be converging faster than the orange one, although there's some kind of strange behavior where it's not as smooth. It's a bit jagged, and you can see over here, like it seemed to have been settling, but then actually the cost went up. And so even the green one is behaving a little bit strangely, but we can make it behave even more strangely if we just double the learning rate with respect to the green one, and now you get this really crazy behavior. And you can see the effect of making the learning rate too big, which is you're going in the right direction, but you overshoot where you want to be, and you've actually made the cost way larger. And then, okay, maybe it recovers a bit, but then you overshoot again, and so on. So this eventually seems to kind of settle down, but probably if you zoomed in, you would see that it might be doing some more weird stuff in there. So at the end of the day, if you want to say, well, which one is best, we can look at the test accuracies. And we see that the lowest test accuracy was from this 1e minus 4, 97.5. Actually, yeah, that's the lowest. And then second best was the red one, 97.8. Third best was 98. Oh, actually, let's see. No, I said this all wrong. So we want to maximize accuracy. So the best one was 1e minus 3. That has the highest. Second highest was the red one. And third highest was the orange one. Okay, so this seems to be the best, at least of those ones that we tested. Okay, so any questions on this? All right, so, but maybe we could do better. Like, maybe there's a way of actually adapting the learning rate as we go. Yeah?
So for the previous one, we do not potentially add a tolerance if we don't have to evaluate for 1,000 steps.
That's right. Here we're just evaluating for a fixed number of steps. We could also set a tolerance, a stopping condition on the algorithm so that when the performance gets below a certain threshold, we stop it there. So that's certainly something we could do. We're not doing it here. We have to be a little careful in how we how we decide on the tolerance. So we might, want to. You could, for example, look at how much change you see in the parameter vector W from iteration to another, or you could look at something to do with the test accuracy itself. So there's a lot of options there, but it's certainly something we could do. But for right now, we're still focused on this question of the learning rate. Like, is there something better than just choosing a fixed learning rate and trying different ones? So we're going to try an adaptive learning rate. Is there a way we can adjust the learning rate on the fly so that at every iteration we can say, yes, this is good, or I should make it bigger, or I should make it smaller? So there's many different approaches to this. And this is one pretty nice one called the Armijo Rule. This works well for convex functions, but I would not use this for a non-convex function. So the Armijo Rule can be understood, again, by starting with our equation. This is our Taylor series expansion that we got for the cost j. So here's our reference parameter wk, and then the new point we're testing is w iteration k plus 1. So again, our goal is that this new cost is as small as possible and hopefully smaller than the old cost. And we have these two terms. The middle term is helping us to decrease the cost, but the last term is actually hurting us. It is increasing the cost. And so we can make a little plot, perhaps. This is useful. So if I plot this versus alpha k, we get something like this. So this is going to be j. This is my cost after my update as a function of my step size. And if I use 0 step size, then I would just stay where I was, and this would be JWK. So what you see here is that for very small alpha, you can essentially ignore this, and you can say that the cost behaves linearly in alpha, and this would be, essentially this would be the slope. So you could say there's going to be approximately linear behavior there. But once you start increasing alpha quite a bit, then this other term will start to take over. And eventually, this will overwhelm this, and that's the situation we're in here. So eventually, we get some kind of quadratic in alpha behavior. So as you can see from this, if I want to choose a step size, alpha, well, any step size in this range will decrease my new cost with respect to my old one. But obviously anything above this is bad because my new cost is worse. But I don't really want to be over here. I'd ideally want to be somewhere down here. So how do I select the alpha so that this happens? Well, so the Armijo Rule is a pretty clever way of doing this without too much extra computation to figure out a good new step size. And essentially what it does is it comes up with a rule that either you pass the rule or you fail the rule. If you pass the rule, you say, that was a good step size for now. I'm going to accept my gradient descent update, and I'm going to move on. If you fail, you say, okay, that was a terrible step. I'm going to pretend it never happened, and I'm going to try again with a lower step size. So the rule that it implements is to check whether your new cost is less than or equal to your old one minus some adjustable number c times this term. Okay, so again, this looks just like this, except you have this number c in there. C is a design parameter. It has to be between 0 and 1. Usually people just choose it as 1/2. So we can now draw, essentially, there's another line here that has, so if c was 1, you would be at this line, but if c is 1/2, then you have a line with half the slope. So half the slope. So again, the test is, if your new cost is below the green line, you accept it. If it's above the green line, meaning anywhere over here, you reject it. So this essentially would tell you to accept anything in this region. So that's the Armijo Rule. So again, in the Armijo Rule, what you do, you have a hypothesized alpha k. You take a step. Now you know your wk plus 1. You evaluate the cost of wk plus 1, and you compare it to your old cost as well as this other term here. And if it's less than or equal to, yes, the rule passes. You accept your update. If this fails, you reject it. You say, I'm going to try again, but I'm going to try again with a different alpha k that's smaller, because I was probably somewhere over here, and I need to try again with a smaller alpha. So that's essentially how it works. If the rule passes, you accept. If the rule fails, you reject. Now, there's one more thing. So we said if the rule fails, you reject, and you try a smaller step size. So the typical way that's done is you have some decrementing constant, less than 1, maybe it's like 1/2 again, and you just say, my new step size is going to be 1/2 of my old one. And that will decrease your step size. But you could also say, well, maybe even though I accepted, I had a successful rule, maybe my step size is way too small. So how do I move out of this region? Well, I have to be more aggressive. I have to try to push the boundaries. And so anytime things pass, we're going to try to be more aggressive the next time. So we're going to actually increase our step size. And it will keep increasing and increasing and increasing until you start failing, and then it will knock it back. And then eventually you'll be kind of oscillating between passing and failing, but you'll always have a step size that's just kind of at the maximum to make progress. So that's the full Armijo rule. When you reject, you decrease your step size, but when you accept, you become more aggressive the next time. Okay. So any questions on the Armijo rule? All right. So there is another approach called line search, which is going to be more work. It's more expensive, but it's going to give you a better result. So in line search, what you would do is you would actually just try a whole bunch of different step sizes before you choose any of them. So maybe you choose all of these, and then you say, which of those step sizes gave me the best result, and you choose that. Now, the reason why this might be less desirable is that in the work that it takes you to evaluate all those step sizes, before you ever used any of them, you could have made a whole bunch of steps with the Armijo rule or some other rule. You could have made progress. So line search is like you're really trying to be very picky about finding the perfect step size, but in doing so, you're wasting a lot of time where you could have actually been making progress. So line search is definitely a popular thing, but just want to understand, why we might want to use Armijo instead of line search. So it's more accurate, but more expensive. Okay, so this is essentially the picture that I drew on the previous page. I don't think there's the only thing to consider here is the choice of C. Previously we said often C is 0.5, but now we can actually understand the effect of using a different C. Let's say I use a C that's closer to 1. Now I'm going to get a line here, and I'm going to only pass when the red curve is below this line. So that's going to narrow my range of admissible alphas, and that's probably not optimal because, number one, it's going to be harder to find an admissible alpha, and number two, the alphas I'm choosing don't actually decrease my cost too much. On the other hand, if I expand alpha k larger than 1/2, then I have a line something like this, and it's easier to find an alpha that works, but now a lot of my alphas are less productive than if I was down here. So for that reason, people tend to use a constant C of about 1/2. Okay, I've gone way over time. Sorry about that, but let me just present this one last slide. So here in this last slide, we can see what happens when we do our Armijo rule. The cost is decreasing very nicely. This is the learning rate. You can see we kept increasing it. We were more and more aggressive until it failed, and then we knocked it back until it started working, and then eventually it just started oscillating, but it was kind of honing in on a really good value. And actually what's interesting is it started to increase towards the end. And finally, the accuracy we got is better than the best step size previously. So it seems like this has been pretty successful in this logistic regression problem. So again, sorry I lost track of time today. Got really excited about Armijo Rule. So any last questions before we go? Okay, great. So midterm exam is going to be here in this room on Friday. So when you come in, just, I think probably the room is going to be pretty full. Remember, there's no electronic devices. You can bring in your cheat sheet with stuff written on both sides. And if there's any questions, just post things to the discussion boards or come to office hours or ask the TA. Okay, see you guys on Friday.